I guess what I'll be talking to you today about is pretty much the focus of my entire research group is, what might we add to a future implementation of some form of hardware quantum annealer, maybe based on superconducting or atomic systems, which allow us to go beyond the transverse field Ising model in some way which might help us do quantum annealing. So my name is Paul Warburton. I'm at University College London, and here's the format of my talk. So I'm first going to talk about how we might enhance the gap by strategically adding various higher order XXX catalyst terms to our quantum annealing system. We heard some of this from Roopayan in the first talk this morning. We'll hear more about this from Natasha on Friday, so that'll be fairly quick, I hope. I'll then move on to talk about how we might implement these XX terms using only X, Z, and ZZ terms that we already have on, for example, the D-wave quantum annealer. That's work that's done by my former PhD student, Bobby Banks. Then I'll talk about how we might move towards implementing these XX interactions using some of these ideas on a neutral atom system. I'm glad that Nick, in the previous presentation, pointed out the true meaning of the word towards, in case you were not aware of that, and it does a lot of heavy lifting here. And then I'll finish with some conclusions. Okay, so first of all, why do we want to add these higher order XX and XXX terms as catalysts in quantum annealing? And that's really about, as again Roopayan explained, getting through the minimum gap without exciting to an excited state. So here's an avoided level crossing. This is a perturbative crossing, which typically happens quite late in the anneal. And in order to transition between some state A, which we're in the ground state before the avoided level crossing, to some state B, which maybe is going to be the ground state at the end of the anneal, we're limited by this gap. And to first order, if we have a standard X driver, the standard X driver only couples states which are separated by a Hamming distance of 1. And so that's what, the tunneling between these states A and B is what determines this avoided level crossing gap amplitude. And therefore, in order to enhance the minimum gap, it seems believable that we need to add nth order XX or XXX catalysts, which will then couple states that are separated by a larger Hamming distance or a Hamming distance of n. And that's what the basic idea behind this is. And in particular, we want to ask this question, can we enhance the minimum gap in quantum annealing by adding some kind of higher order driver, most importantly with no prior knowledge of the state spectrum of the annealing spectrum, because that will be cheating. So this is the focus of the work that my former PhD student, now postdoc Natasha Feinstein, has been working on. Here's a reference down here, and again, she'll be talking on Wednesday at this conference. And she's done a lot of work based around, again, as Roopayan explained, this bipartite weighted maximum independent set idea. I've got the wrong headline here. This is not a single XX catalyst. It's an XX catalyst, and the number of XX pairings we have scales linearly with the number of qubits. And again, just to clarify, this is an idea that we took from the work of Vicky Choi, who's done a lot of work on this particular problem setting. And if you look at the simulated graphs of the energy gap minimum as a function of system size going out to 39 spins in this case, if we don't have a catalyst, we have this very nasty looking exponential scaling of the minimum gap. If we add some catalyst where the number of catalyst pairwise terms in the Hamiltonian scales linearly with the number of qubits, and we optimize the strength of this interaction, this XX interaction in the form of a catalyst, we get a significant enhancement of the gap as shown here. So that looks pretty good, and furthermore, if you look in the inset here, this is a graph of the optimum value of this catalyst as a function of system size. And you can see there's a suggestion that as the system gets larger, this optimum value of the catalyst is tending to some scale-independent, size-independent value, which means we can just take that XX interaction off the shelf and not have to optimize for every individual problem. Of course, this is just with a toy Hamiltonian to illustrate some of the features, not so useful as a real problem. As Roopayan explained earlier on, we can extend these ideas to randomly generated graphs. This is work done by Luca Nutricati. And this is on 10,000 randomly generated Erdős-Renyi graphs with 10 spins and a probability of a pairwise link between any pair of spins equal to 0.6. And here we're plotting on the y-axis the minimum gap with this XX catalyst, and on the x-axis the minimum gap without catalyst. So we want to be above this red line, and you can see that each one of these dots corresponds to one of the 10,000 randomly generated instances. The majority of instances are on the good side of the line, suggesting the addition of the XX catalyst is doing a good job. And furthermore, if we look at the inset, this is a plot of the ratio of the catalyzed gap to the uncatalyzed gap as a function of the uncatalyzed gap. And this, in my personal view, is the really good news from this plot. What it shows us is that the most difficult problems with the smallest uncatalyzed gap have the biggest enhancement of that gap when you add these XX catalysts. And again, I think Natasha will be talking about similar ideas on Wednesday. So I guess Roopayan spoke about this significantly in his presentation, but this is basically showing you can extend these ideas beyond the quadratic XX catalyst to a cubic XX catalyst and indeed higher order terms. Okay, so that suggests that by adding XX and possibly XXX terms as catalysts to our annealer, we can enhance the minimum gap, increasing the likelihood of ending up in the ground state at the end of the anneal. But how do we implement these ideas? So at the moment, if you're looking at the D-wave machine, for example, which I think it's fair to say is probably the state of the art for quantum annealing in hardware right now, we have only access to X, Z, and ZZ terms in the Hamiltonian. So what are we going to do about this? So here's the problem. This, in this blue cloud, is what we have at our disposal on the D-wave. And we want to achieve all those things in the Hamiltonian plus something that looks like an XX interaction using only these three native X fields, Z fields, and pairwise ZZ interactions. How do we do it? And this is work, as I said, that was done by my former PhD student, Bobby Banks. So the general approach is that we want to add some ancilla qubits to increase the size of the Hilbert space. And then we add a penalty term, some form of constraint, that partitions this enlarged Hilbert space into some low-energy subspace where the constraint is satisfied, and then a high-energy subspace in which the states don't satisfy the constraint. And then the third stage is to implement fields which we have at our disposal, so X, Z, and ZZ interactions on the physical qubits, so that the effective Hamiltonian on the low-energy subspace contains only these logical X, Z, ZZ, and the additional XX terms that we're interested. So it's the logical low-energy subspace where the states satisfy these constraints, where we can ideally get an XX term as well as our X, Z, and ZZ terms. Okay, so if you look at Bobby's preprint, there are two ways of doing this, and we also have a patent application in the United Kingdom for looking at this guy, which is the truss gadget. In today's presentation, I'm only going to talk about this guy, which is the so-called one-hot encoding gadget for implementing XX interactions using only terms that are natively available on the D-wave, for example. So what is the one-hot encoding gadget? We basically add some ancilla qubits, and now we have 4 physical spins, and we encode the, so this is to encode 2 logical spins, and you can see we have this one-hot encoding where each of the 4 logical states is encoded by 3 spin up, 1 spin down in the physical state. So it's basically the location of the spin down, shown in red here, which is encoding which logical state we're in. And in a very sort of qualitative way, you can see that if you can implement a logical X in this system, then the logical X requires 2 spin flips. So for example, going from 0, 0 to 0, 1, I have to flip both of these spins. And that is the same number of physical spin flips in a logical XX. So for example, if I want to go from 0, 0 to 1, 1, I still have to flip 2 physical spins. So if I can implement a logical X, then I can probably implement a logical XX as well, because they both involve two physical spin flips. So that's a very hand-wavy argument to why this might work. More details are in the preprint, and here I'm going to gloss over some of these. So first of all, we need a penalty constraint that ensures that we're in one of these physical spin states. That's reasonably straightforward with a term like this in the Hamiltonian. We then add local X fields to give us this physical Hamiltonian of our one-hot encoding gadget. And if you then find out the effective Hamiltonian for the logical states which are in the low energy subspace where this penalty constraint is satisfied, you find that you have an X term on each of your two logical spins, and most importantly, this XX interaction. And just to note, for those of you who are interested in the topic of stochasticity, the XX term is always negative in this case. Okay, so that suggests that I can have an XX term in the following fashion by adding two ancilla qubits to my two logical qubits. I also want to, of course, encode my longitudinal Z and ZZ terms. I'll spare you the details of these. You can look at the preprint, but essentially, in the physical system, you have quadratic interactions here, you have an X field, and then you have some one local terms here, and that gives you this effective interaction for your logical qubits, including this XX term, your local X drivers, plus your longitudinal terms in the standard Ising form here. So that seems to work. Now let's think about whether this is actually helping us in terms of our gap enhancement. So again, we're returning now to our old friend, this bipartite weighted maximum independence set problem. And we're going to solve this three ways. First of all, using the standard linear transverse field driver, single X driver on the physical qubits, logical qubits, I should say, I guess. We're also then going to assume we have a perfect XX driver and add that, as shown here, on one half of this bipartite maximum independence set, just a single XX driver. And then finally, we're going to use this one-hot encoding to replace the XX driver on this pair of qubits here with these additional two ancilla qubits as shown here. So now here's the result. We're just doing exact diagonalization to calculate the gap in those, the minimum gap in those three cases. So here for a system of, I guess, 21 spins, we're plotting the minimum gap on the y-axis on a log scale as a function of the normalized annealing parameter running from 0 to 1 on the x-axis. With the standard linear transverse field driver, we have this horrible minimum gap at about s equals 0.7 something, and that's the gap which is going to cause errors in our computation, so we need to eliminate it. And we can eliminate it quite successfully with this additional XX driver. So if you assume you can just take an XX driver off the shelf, that rather successfully eliminates this gap minimum here. With our one-hot encoding, we take a hit overall with the overall scaling of the gap energy, but we have eliminated this gap, and in fact, everything scales just linearly by comparison with the XX driver. So it looks like the one-hot encoding is working with this proviso, of course, that you take a hit overall. So the real question is what is happening as I scale up to bigger system sizes. So this is now the gap minimum as we scale up to, I think, 39 spins in this case along the x-axis. With the standard linear driver, we have this exponential scaling. If we can magic an additional XX driver, we get rid of that. And with the one-hot encoding, we follow the same scaling, notwithstanding this prefactor. And so you can see in this particular toy example, for system sizes bigger than about 20 qubits or so, we get an improvement in the minimum gap from our one-hot encoding. Okay, so that seems to suggest that the XX term could be useful in enhancing the gap. And furthermore, using this one-hot encoding technique, we've got a way of sort of spoofing an XX interaction using standard terms in our hardware toolkit. So Next question is, well, let's try and implement this on the hardware then. And here's the magic word, towards. So we're looking about how we might implement this XX interaction using this one-hot encoding on a neutral atom system. So this is a collaboration between my group and the group of John Pritchard in the University of Strathclyde. And what I'm going to talk to you about now is Natasha Feinstein's work on simulating how that system might run. And we're hoping to run it on a real system in the near future. Okay, so here's the simplest instance of a one-hot encoding. We have 4 physical qubits, and we're going to put this on a Rydberg atom system and put the atoms on this square. And what you find is that you can write down the Rydberg Hamiltonian based around this interaction V between the atoms, where n is the number of Rydberg states for each atom. So you can write down this Hamiltonian, and what you find, which is, I guess, needs some attention, is that the states with 0 spins down and 1 spin down are degenerate. For a one-hot encoding, we clearly are not, we're only interested in physical spin states where the total number of spins down is 1. And so we need to eliminate this degeneracy by adding some local longitudinal fields, which we can do fairly straightforwardly. So this gives us the overall Rydberg Hamiltonian. Here's our pairwise interactions from the Rydberg system. We then add a local field here from this detuning term delta, and then we add this Rabi term here, which gives us these X fields in the Rydberg system. So that's our physical system for these 4 qubits. And if you look at the low energy subspace, which is within our coding subspace, what you find on the 2 logical qubits is the following Hamiltonian, where you have an XX term given with some weight B, and then you have marginally annoyingly unequal terms on your 2 atoms, essentially because arising from the fact that the diagonal interactions in your 4-qubit physical system are not the same amplitude as your along the edges interactions. But nevertheless, we have a logical Hamiltonian containing this XX term arising from standard terms in the Rydberg Hamiltonian. So what Natasha has done now is simulate the time evolution of that physical system and compared it with what we would expect from again, an assumed exact XX interaction. So we're initializing in the down-down state, and now we're plotting the probability of any particular state as a function of time along the x-axis. The dashed lines are what you get from an exact XX interaction, and the solid lines are what you get from our simulation with this one-hot encoding. There's a bunch of parameters across the top, which my atomic physics colleagues in the University of Strathclyde tell me are realizable. And so you can see that this one-hot encoding reproduces with pretty good fidelity what we expect from an exact XX interaction. And we're looking forward to running this experiment with our Strathclyde colleagues in the near future. So I've reached my conclusions. I've shown that we have some deterministic way of enhancing the minimum gap using an XX catalyst, at least for a toy maximum weighted independent set problem. For more general random graphs, we've shown that at least we have a heuristic gap enhancement using quadratic and third order XX and XXX catalyst. We talked about ways to implement at least an XX term with a negative sign using these standard Ising terms plus ancilla qubits. And we've shown that with this one-hot gadget for the XX, it looks like we can think about implementing that on a neutral atom system in the near future. Here's a picture of various people who worked on this collaboration, some of whom are in this room. And finally, I should acknowledge the funders. This was supported by the United Kingdom EPSRC through the QCI3 hub, which is led by the University of Oxford. And if you need to know more about anything I've said today, then here are some papers where you can look it up. Thank you very much for your attention.
Thanks. It's time for questions. Yeah. Oh, okay. Yep. We're faster over in this side.
Hi, thanks. Interesting talk. Just a question about this scheme. It seems that the XX interaction is somehow locked to the X interaction. Does that make a big difference, or does that somehow limit things, or do you have any thoughts on that?
So I think certainly in the Rydberg implementation there is that coupling with the X term. I don't think necessarily that's the case. That one could imagine doing it with superconducting qubits in a way where, I think I'm right in saying this, that they're decoupled. Is that limiting? Potentially, I guess, but we really haven't studied that in detail yet.
But even in your scheme with this encoding, it somehow they are somehow fixed together. You have this B term out in front of both of them.
Yes. No. Okay. That's a fair point. Yes. Yes. You're right. Yeah. I don't know.
But it seems to. I mean, you still get an improvement even with that.
Yeah, we certainly get a gap enhancement. I guess given that this is just in the catalyst term, it doesn't limit you in terms of what problems you might be solving. So as long as it's doing some good to the gap for your problem, maybe this is not a limiting factor.
No, it's interesting because there's a kind of way to do this with superconducting qubits, but you would have this kind of limitation. So it's interesting to see that it still gives you improvement. Thanks.
Sure.
Thank you. So when you have a catalyst, basically you switch it on during the dynamics, right? So it's switched off both at the beginning and at the end. So I assume the driving is the usual S times 1 minus S here. But how critical is the choice of the scheduling of the catalyst? So if you knew like where the perturbative crossing happens, can you even just switch it on and off in that region? Like without having the S times 1 minus S?
Yeah, I guess you could. I mean, that's clearly something we don't know. I guess in the simplest instance of an answer to your question, clearly if you can vary your annealing rate through some gap minimum, then I guess you can go fast elsewhere and then slow down and then go fast elsewhere. So that would help. And I'm guessing that if you also apply similar ideas to the catalyst, that you could locally in time, as you're suggesting, enhance the gap only when you're going through it. I'm not sure what that would buy you. There may be some benefits, but
yeah, no, I was just thinking that in the Rydberg case, maybe you could implement it as a gate-based stuff. Like because usually in Rydberg you can also implement gates with pulses. So in principle, you could be able to implement XX gates, like just by implementing.
Yeah, certainly. So again, in Roopayan's presentation, he was talking about trotterizing these ideas, which certainly works. It's a big if to know where that avoided level crossing is. But I guess if you did, then you could apply the gate. Or yeah, sure.
So this one-hot encoding gadget, does it also work for implementing an arbitrary number of XX catalysts, or just one?
Yes. So there are details in the paper of how you can extend this. I mean, certainly in the paper, it's all in the context of the bipartite weighted maximum independence set, but it is, I believe, generalizable to multiple XX.
Okay. And do you know how the required number of ancilla qubits changes with the number of catalysts?
So to implement a single XX, you need 2 additional ancillae. I guess the easy example is if you have, let's say, 2 XX interactions with qubits that are not shared here and here, then that would be a trivial scaling. I'm not sure if you have a single qubit involved in more than 1 XX interaction, maybe it gets more complicated, but I'm not sure.
Okay, thanks.
I think Dr. Feinstein has an answer to that question.
I was just going to throw out an additional detail, which is if you can only drive...
Do you want to get the mic, Natasha?
Okay. Yeah, I mean, that answer was basically correct with the additional complexity that if you can only drive homogeneously, like if you can only drive your physical qubits homogeneously and you want to preserve that homogeneous driving when you move to your logical qubits, the total number of qubits needs to double rather than just replacing the 2 you want an XX coupling between with an additional 2. But yeah, apart from that, if you could drive inhomogeneously your physical qubits, you would only need to double the qubits you wanted your XX on.
Thanks, Natasha.
We might have time for another question because there was a raised hand here. If not, if it's not there anymore, then you guys are free to go to lunch. We'll be back here at, well, let's thank Paul again.